couple weeks ago, and second time is here. And he is actually the PhD in engineering, although he is right now teaching in the School of Public Health. And the most important specialty is about the flow control, about the ventilation, about the indoor air quality, which is very related to our topic. Recently, we just have a certain kind of the idea about the environmental monitoring device, that kind of thing. So we would like to invite Dr. Chen come over to here to give a talk. And then now we give a big pause to
dear professor, dear classmates, I'm Jia-Kun Chen. Jia-Kun Chen from the Public Health. Thank you for the invitation of IPCS, so I can come to IPCS today and share my research. This is my resume. I will give you a brief introduction about me. I am a PhD of engineering, and I focus on the research of flow control, indoor environmental control, and ventilation. And also, at the same time, I serve in the public health. Why does an engineering PhD work in the School of Public Health? Because there's a field of environmental and occupational health research in public health. In this field, ventilation is a very important and practical knowledge. And the basis of ventilation is the fluid dynamics. So that's why existence no longer so strange. So that's why I am a PhD of engineering, and I work in the School of Public Health. First, I will show you the training of engineering. At the beginning, we will start the existing problem here and give us a systemic analysis. Usually we choose this way or this way. This way is improvement. Then the method of improvement, if the improvement is appropriate, the problem will be solved. But however, after most of the problems have been improved, other problems will arise. Therefore, after a long time, the people behind will accept the fact that the performance of the system or the tool cannot be improved for the reason that the previous people did. But why not to choose another way to develop a new tech to solve the problem at the initial stage? In engineering training, when we solve the problem with a new tech, we will develop the prototype. When we develop the prototype, we try to make the prototype to become the product and save the world, make a lot of money. This is my research topics. My research topic is based on the fluid dynamics, which divided into two parts. One is industrial hygiene, and the other one is indoor air quality. In the field of industrial hygiene, chemical film hood is the representative of local exhaustive ventilation, and the range hood is the representative of local exhaustive ventilation in indoor air quality. Today I will introduce two things to explain how to engineer to solve the problem of public health. Indoor air quality. Range hood is the representative of the local exhaustive ventilation system in the indoor air quality, especially in your house. Cooking oil fan is the most important pollutant in your house. This is a review paper describing the research on the lung cancer and on the relationship between the cooking oil film and the lung cancer. Lung cancer is a very important public health issue. cooking oil fin has been identified as one of the causes of lung cancer. When the temperature is high enough, then the smoke point, when the temperature is high more than the smoke point of the oil, cooking oil will produce carcinogens. So smoke point refers to the temperature at which oil starts to burn and smoke. However, public health scholars will tell people that oil fin is easy to cause cancer. So please avoid excessive exposure to oil fin. However, in reality, it is impossible for us to ask people to avoid the exposure of oil fin. You will also expose your oil fin if you go to a restaurant to eat, even if you don't have a cook in your house. You expose more oil film than at home because of poor ventilation in the restaurant that you stay. Generally speaking, we have the three ways to prevent the oil film exposure. One is cooking without oil. The other one is personal protective equipment. This is the famous after COVID-19 because generally speaking, we use the mask is a kind of PPE. The other one is the ranger hood. The ranger hood is the most solution of engineering intervention in public health in your house to avoid the oil film exposure. But cooking without oil, the cooking method might not be suitable for everyone, and different cooking methods will give food different flavors. So cooking oil is an idea, not the actually action for people. And wearing a mask, a kind of PPE, this is a way most people present. But have you found that wearing a mask can you still smell oil smoke? And it will increase your fatigue during cooking. And the ranger hood. And the ranger hood is the engineering intervention. And in this speech, I will introduce how to solve the problem that we found in ranger hood studies. Do you have a similar situation? You have used the ranger hood, but you still find the kitchen oil film is sprayed, and the kitchen is hot, and the wall in the kitchen are greasy. Because there are 5 floor dynamics design problems in the conventional ranger hood. So now we are going through the fluid dynamics. We have 5 problems in local ventilation system. Ranger hood is a kind of a local exhaustive ventilation system. First problem is effective capture velocity. Second problem is the block body weight. Do you have a class of fluid dynamics?
Some of us, we have some of us.
Okay.
Some of us is major in the Department of Atmospheric Science.
Okay. Fluid dynamics is okay.
Some of us don't.
Okay, block body weight. This is the body. This is you. This is me, who cooking in front of the ranger hood. Third, effect of drag. Third, fourth, boundary layer separation. And 5, flow power air moving devices. That's 5 problems. Okay, first, effective capture velocity. The characteristics of suction is that as a distance from the suction inlet is farther, the suction velocity will drop quickly, like this, like the data showed in these figures. If the diameter d of the suction inlet is taken as a unit, the suction velocity here is only 1.5% of the suction velocity inlet. Here just 1.5% of this. It is far away from 3D. It means if we cooking here, the distance from the oil pan to your suction inlet, if the distance over 3D, the D is the diameter of this suction inlet. The suction velocity is just 1.5% of here. Actually, it means the range hood installed in your house, it doesn't work. Why? Because the distance is too long. The range hood is too high to catch the oil film. So everyone has the experience in using vacuum cleaner. The vacuum cleaners are in use. We always put the suction inlet close to the garbage that we want to suck. We will not move the suction inlet away from what we want to suck away, right? But please see the video. See the oil fan. As the two-picture video has a result of flow visualization. The flow visualization is a kind of technology in fluid dynamics. This kind of technology try to make the flow can be visualized. See the oil fan in this conventional range hood. See the oil fan is sucked, but the flow pattern is unstable. And see this. There's a plume. This location is close to the human's breathing zone. So that's why you always smell the oil film when you use a range hood. The second problem is block body wake. This is a mannequin. To simulate a real guy to do the cook in front of the range hood, in front of the range hood. See this? That's why you smell the oil film, always. This is block body. This is your shoulders. When we stand in front of the range hood, the airflow comes from behind. And the wake is formed in front of our chest. And the wake has the low pressure in the center. Flow moves from high pressure to low pressure. So that's why the pollutant from the high pressure to low pressure. From the high pressure to low pressure. That's why you smell the oil film. And this is the flow in front of your chest. There's a wake. There's low pressure here. So pollutant will from high pressure to the low pressure. Third, the effect of draft. In the kitchen, when the suction velocity is insufficient because the suction inlet distance is too high. The oil film will spread throughout of the kitchen. At this time, we usually open windows to increase the air circulation. And at this time, the environment will have an unstable cross-drift. Please look at this picture. We have, this picture is actual major vector figures. This is dividing line, the dividing string line. Above the dividing string line, the flow here just get into the suction inlet. But under the dividing string line, the flow here just go to the right side. This is the flow visualization. That's why oil fin will spread out if we open the windows to make the air circulation well, but at the same time, open windows also break the floor of the range hood. So when you use a range hood or cooking in the kitchen, please close the windows, and please do not stand in front of the range hood, and please do not cook in front of the range hood, and that will make you to avoid the oil fin. It means you can use the Uber Eats or Foodpanda, but do not use the kitchen, okay? Because this is a naturally fluid dynamics parameter. If you use a suction inlet there, this flow will make you expose more oil fin, and more oil fin will might be added the risk of lung cancer. And this is the flow separation. Sorry. This is the flow separation. This problem occurred when there are walls around the range hood. Why we have the wall around the range hood? Because someone think that the range hood has a sidewall because someone want to use a sidewall to block environmental disturbance. But when the sidewall is used to block the environmental disturbance, more leakage will occur due to the characteristic of flow separation here. So the small oil here, if we have the walls, the separation will here. And the center of the separation is low pressure. The flow will flow from high pressure to the low pressure. That's why the pollutant will be moved in from the pollutant inside the range hood will be moved to the in front of the range hood. And the last one is the choose between flow rate and the system impedance. Simply, it is the choice of fan. This is also the easiest way for everyone to choose. Anyway, an oil fan will leak because the flow is not enough. I can solve this problem by increasing the flow. General people think. Unfortunately, the oil film still leaks. So, if you have a problem of a catch velocity, increase in the flow rate, block body, increase in the flow rate, effect of draft, increase in the flow rate, flow separation, increase in the flow rate. The final thing, increase in the flow rate. This is what we call improvement. But still leaking, energy consumption. So we will rebuild a new range hood. That's the positive thinking. That's the negative thinking. Okay, according to our research, slab inlet has a long effective suction distance more than the circular inlet. See the two pictures. This is the picture in previous slides. The flow here is unstable, but in these conditions, the flow is stable and suck it into the suction inlet. And we have the long effective distance more than the circular inlet here. Boundary layers separation control. The idea is using a sidewall to block wind is not wrong, but the flow separation makes the leakage worse. Is there any way to change the position of the flow separation? From here, and from here, move inside of the range hood. We design a different boundary layer separation controller. We use a kind of flow phenomenon called flow reattachment to successfully move the position from here to the inside of the range hood. And the oil fin in the kitchen is high temperature oil fin. High temperature will cause gas to extend, so high temperature oil fin is not easy to control. But when we use something interesting, we design a slot jet on the upper edge of the range hood to generate an isolated bubble. We have a slot jet here. See, there's no slot jet. There's a slot jet. So very clear edge here. And this is the isolation bubble. The high temperature oil fin move up and be controlled by the slot jet that will stand in here. And the slot suction here, we will suck the high temperature oil fin out of the kitchen. So using such a flow field, we can check the gas that expanding due to temperature and use the momentum of the jet, bring it down, and it will not escape from the top of the range hood. And this is the prototype. It's a range hood, right? It's really a range hood. Made by papers. Really papers, not just the publication, okay? It's the papers, yeah. But the thickened papers. And because of our design, so there are 4 tornadoes in the flow field inside this range hood. So we named it inclined core vortex range hood. The idea is this. The center of a tornado is a low pressure zone, right? So every oil fin is controlled in the low pressure zone. And in this space, this is the low pressure zone. So that will be sucked here. Here is a high temperature gas, so the suck will easily to bring the oil film into the suction inlet. And the suction inlet just installed close to the wheel wall, so the flow will be inclined. So there is no oil film here around the human's breathing zone. So this is the vortex structures. So we have 4 tornadoes in the range hood. Use this kind of flow phenomena, we can control the oil film spreading. So that's called flow control. Control flow, make the flow the way that you want. In previous slides, are based on the flow visualization. In order to ensure that the oil film is really not leaky, we conduct a tracer gas test. The picture on the tracer on this slide show set out methods of our tracer gas, and each white part is a sampling probe. So we totally have total of 8 samples around the range hood, and this one is a comparison with the traditional one and the innovation one. Please focus on this. See the order of the value. So means there's no leakage, almost. The unit is ppm. And we use the low flow rate to make this possible. The conventional one is use the 10.5 cmn. We just use 9.4 or you can use 5.8. There is no human body here. And then we put a mannequin to simulate the body. And take a sample probe around the breathing zone. This is the answer. See? Almost no leakage. Sorry, this Chinese is if you have a suction and you can effective to move the pollutant, but if you use more flow rate, it means the more effective. See, the conventional increase the flow rate, but leakage becomes serious. Why? Because that is in a wrong aerodynamics design. This is in a correct aerodynamic design. We find a research of Harvard University. He also get the same answer in the leakage of the exhausted cabinet. Increase the flow rate, leakage increase. So what does it mean? It means that there is nothing wrong with our previous research results. Simply increasing the flow rate cannot solve the problem of oil film leakage. And this is commercialized range hood. I have one in my house. It works very well, but it costs a lot of money. Really. Okay, industrial hygiene have the same problem. The chemical film hood, we also use the flow control technology to redesign a film hood. This is the conventional film hood. When you use the conventional film hood, you have the same problem: leak, and leak. No one standing in front of a film hood, the oil film leaking. Someone run fast in front of the film hood, leak it a lot. When you do some experiment in front of leak, open the station, leak it a lot. So that's why we call the junior student to do the experiment. Why? Because you have a healthy body to burn, okay? Or you have some complaint with your senior student. When your senior student do the experiment, you run fast along behind his back. Seriously, okay? So the problem. So we also use the same technology, inclined air curtain film hood, to control the pollutant inside the film hood, not leaking out. Use the boundary layer separation controller to install the BSC under the sash, control flow separation. And we have a standard to ISO standard to qualify the film hood. So we have the traditional one, the liquid concentration is here, and first type. This is our second type. So see the leakage order. So this is designed in a correct aerodynamic systems. And in the left table, when your liquid concentration is average or the mass value in this level, your film hood is just to restore. Okay, this is the standard of America, NC ASHRAE 110. And we also get the low leakage concentration. And that's the product. So that has a lot of companies to have this ritual. Even our school also have it in Department of Chemistry. So conclusion, local ventilation and fluid dynamics has a strong connection. Increased flow rate is not the only solution to solve the leakage. Engineering and public work together perfect. Thank you, everyone.
Anyone have questions? Someone from the automobile science department might have something to say first. Yes.
Because this is interesting things. In my experience, I'm a PhD of engineering. Before I served in the School of Public Health, I just do the research of fluid dynamics. I have no idea about the public health. But when I went to the School of Public Health, I find a new stage. So we are the same people, right?
Yes.
We are engineers, right? We are engineers. We are scientists. Do the technology, do the research. We need a stage. Public health is a big stage for us.
Big stage.
Yeah, big stage. Big platform. Yeah, for us. We can use a lot. Even the professor said you are majoring in indoor air quality. When we measure the indoor air quality, like the CO2 concentration, for what? For engineering, we just want to control the concentration of the CO2 under 600 ppm. But in the AP of public health, AP means the epidemiology. We simulate that. CO2 is an index to see the ventilation efficiency of indoor air. And if you have the poor ventilation, it means in this room you have high risk of airborne infection, like COVID-19. That's the connection. But the purpose, because we are engineers, there's no one work except me, no one work in public health. Because public health, people in public health just has the idea to give the question, to give the problem, give anything, but they don't solve the problem. They just analyze the problem. So I think that's a new step. We have a video.
Yes.
I cannot say this. Videos.
Because we are scientists and you are engineers.
So that public health is a new field. And not a new field, it's a great field.
Platform. Okay. Anyone has something to say?
Okay.
Professor Fishball.
Yeah, thank you, Professor Chen. I think I got a lot of information from your presentation. Because recently we just checked the data in the B105 classroom in the Department of Atmospheric Science. Yeah, it's very quite interesting. So we found that the increased speed of the CO2 concentration is very high related on the open window or not. But actually, we don't know what we can do in the future. How do we solve this problem in the future? Because until 2020, this classroom we also installed the heat exchange system. But the CO2
It's expensive, right?
yeah.
But it doesn't work.
Cheaper one.
So in this classroom, in B105 classroom, we have the three different machines. The first one is the air conditioning, the very traditional, very old one. The second is we install a vacuum, and that's the vacuum, the 抽风机 vacuum.
就是 fan.
Oh, yeah, okay. In the maybe in 2010, but it's not working. So finally, in this year, we installed the heat exchange system in this classroom. But however, the CO2 concentration is still very high, over 1,000 ppm. So actually, maybe in the future, we still want to find some solution in this classroom because it's very hard to solve the problem. Because every student come into this classroom will feel sick. Also the
the same problem we found in Kaohsiung Medical University. At the same problem. And also install the heat exchanger. But it doesn't work. Why? Because the inlet and the inlet and the distance between inlet and outlet of the system is too close.
too cool. Oh.
Yeah, you make the shorten.
Yeah.
So if you have a shorten here, and we have the other circulation under the shorten, it means your concentration will be isolated in this bubble. That's why the concentration of the CO2 is increased, even if you turn on the system of the heat exchange. And then the other problems, if you have a high concentration of carbon dioxide, it means you have a high risk of airborne infection.
Yeah, sure.
Yes. That's the topic of the TB. I don't know how to use it. It's a disease, airborne infection. You have a high risk of the
So it's COVID-19.
yes.
So actually, we try to install some measurement into the common classroom in this campus.
Yes.
So maybe we can discuss more after maybe one semester later. So because some of our classroom in the for example the common teaching building. Actually, when I studied while I'm still in undergraduate, the direction of the classroom is totally different with the previous one. So they change the school, they change the direction of the classroom, and then also to close some wall from the window to the wall or the blackboard. So
I think that IPCS here is a good place. for the indoor air quality. Because you have the tree covered your building to avoid the radiation from the sun, to decrease the temperature from the radiation. You have no high building to block the airflow around the school. Only the point here is just we have an old building, right?
Yeah.
If we have a funding to increase this, will be the perfect research center in school.
Research site.
Yes.
Anyone else?
Okay, I also have some introduction. Sorry.
Yeah.
I have no time to translate it in English. I have a cooperation with Professor Su to measure the indoor environmental quality, and have a cooperation with Professor Ye to build the active green wall system here, and work with the Professor Chen in the public health to explain why this machine cannot capture the mosquito. Because we have the machine have the flow like this. The mosquito will flow this way, then will be pushed out. The machine don't want to kill mosquito, but it's interesting things. And so we also have some interesting study around like this. Open the speed of open the door opening to thinking about the two concentration to cross each other. That is to simulate the situation in the board in the period of COVID-19. So we found this open style has less concentration mass transfer. That's why we have this kind of door in hospital. Okay, that's all. That's all for today.
So I think, although you are in the School of Public Health, but actually you are an engineer, right? So if we IPCS would like to, actually that is exactly something we might thinking about, because we used to be the science and the social science. But for all our applications, we need the engineer.
Yes.
In order to improve many things.
Yes, if you have an idea, you need someone to build a system.
Yes, that is you, right? And then we're just thinking about if that is any possibility. From your viewpoint, most of our students are either science background or the social science background. We have the life science or earth science or the social science, but most of us may not exactly about the engineering background.
Yes.
So if we are thinking about that, maybe one of the possibility for IPCS to develop a new pathway or something. So how the student should prepare in order to work in this engineering field?
Okay, you first because I trained in six students who has a background of public health.
Okay.
And successfully from scholar of public health to engineering master degree. So only thing that we need is you must listen my command. Because I can show you the shortest way to approach the engineering target.
Okay.
And follow this way, you can use the engineering. You just use the short way to approach the engineering, and you can use the engineering technology to improve or to support your science development. It's not a problem, even you have
background.
yeah.
They don't need to know the calculus.
No.
Calculus. They don't need the.
I will show you. Because in this way, there's have a effective training of engineering. Because engineering training, if you have the basis of physics, I think the better. If you don't at school, as students in public health, have no basis of physics, but I can train him because he has the calculus, the best of calculus. If you can read the language of math, and you will approach the language of science.
So the better way is they have the physics.
Yes.
There is the mathematics.
Yes.
But that is not really compulsory.
Yes.
Well, it's so crazy, you know. Any other issues or immediate questions?
Or we can discuss later after the class.
Okay. The way the other one is because all of our PhD students have the Chen, who is it? Chen Hongkai. Unfortunately, his some other business not able to come over to here, but his PhD thesis topic is actually about the 风倒木 is the tree falling down by the wind. Is that it?
Yeah. He might have the pro name, but I just describe it. The falling street induced the wind effect.
So your lectures are more or less about the indoor, but how about outdoor? Wind, speed, directions related to.
Because
how to do that?
in my opinion, indoor is we call it internal flow. Outdoor we call external flow. But they're just in two systems. Internal flow just in a closed system, but external just in an open system. And the phenomena in the two systems are the same.
You can use this one. That is our touchable TV.
Yes.
Just smart TV.
So I think so.
Okay, sure. Thank you.
So like the Honkai's topic. This is a tree, right? And when I have a flow here, so in this way, this is three-dimensional. So I have the low pressure here, right? Low pressure here, high pressure here. So the force will move this way. So it will break this way. So there's the fluid dynamics. There's a kind of multidiscipline. So in the installed flow separation still happening. In the indoor air quality separation also the same.
How can you do this data calculation? How do you know the wind speed?
We can use the computational fluid dynamics. Or we can do the experimental fluid dynamics.
Experimental fluid dynamics.
Yeah, put a model into a wind tunnel to give a uniform wind. So we can get the wind data from the Professor Lin, and we can get the wind of one season and we can simulate the tree under this season wind have some effect of aerodynamics. And we can find a reason why we have the breaking point here. And an improved way we can to give a note to help the workers to how to cut the levers to make the tree can decrease the drag force from wind. So that is the kind of flow control in external flow.
有不要讲吗？有不要讲吗？
那大机器你看的比较大。
I know, yeah.
Because we focus under 1 kilometer.
Yeah, sure.
1 kilometer.
Yeah. But it's higher than 1 kilometer.
Yeah, sure.
It's different scale.
But the model will be the same.
No,
it's
Totally different.
totally different. Because over 1 kilometer, it has a unit of 10 kilometer.
Okay.
But under 1 kilometer, a tree just maybe 20 or 10 meters. So that's total difference. But we always call it fluid dynamics.
Because in this scale, we also use a parameterize. We also use some simple form to calculate the effect of the building, tree, something like that. So actually, we cannot calculate in the all of the detail of the building effect or tree effect.
But they can do.
Yeah, sure.
So your model in the below the 1 kilometer is much better.
Yes.
Kind of like.
Yes, sure.
Okay, so we need you. Okay, anyway. Because to the end, everyone are standing in somewhere below the 1 kilometer, or there is more effect below that, right? But it's like it's something we really need to. I think the model is really important for this research and for many other research as well. We are right now doing about the tiny map. We see the campus, NTU campus, and we have the 15 small, low-cost environmental monitoring device.
Yes.
But the way we exactly try to monitor this kind of the human scale, community scale kind of information. So in that sense, that is your model might be better than the.
I think there's a two-way approach to the same topic.
Two-way. But their information is above 1 kilometer.
Yeah.
Yeah, so I think that is maybe. Anyone have something else? You. Yeah. Your thesis is exactly about the urban city climate map. So, make a comment.
It's good. It's really good.
We should be more than that. Come on.
I thought it's use several sensors to manipulate the urban situation.
In my opinion, I focus on the indoor environment. Why? Because the public health is a science around the human. So I only take care of people
Indoor.
No, not people, but the place has people. That's what I care. If there's just a storage for stuff, so for things, for machines, there's no people. Public health doesn't touch that. Yeah, so people, we spend more than 90% one day in the rooms, even in cars. In your house, in place, in office. So I control the environment, indoor air quality is more important. But the climate change increase the temperature and the humidity, even change the wind direction. Because energy distribution will reduce. That effect the temperature outside and the temperature and humidity will affect the inside. So that's why we need to, from big scale to the microclimate.
And then the indoor.
Yes, that's the continuous mechanism.
So your key point is the microclimate, right?
Yes.
So you also know the permissibility portion quite well. Yes.
Yes.
So how did you see the difference between the one you try to do in the microclimate and then the one they are doing about the climate?
My technology is flow control. I can control the flow inside. If we need this room for 10 people, I can control it this engineering way.
Okay.
If we need the room for 100 people, another control way. So my final target is a small building, healthy building. So we use the control way because I have another target to study the chickens.
Chicken.
Yes,
Chicken house.
yes,
Okay.
chicken and the egg chicken. Because one egg costs $90 annually. One house have 50,000 chickens. So control the temperature, humidity, and carbon dioxide and other pollutant inside the closed system is very important because if we lose control, then a lot of chicken will die. I will lose a lot of money. Chicken just like people, no, people just like chicken.
The same.
We can control this and we work well. We can match a lot of money for organization.
Okay, I think that is really very important, and that is the way we move to the next stage. The climate issues is rather than just only the extremely weather, but also about our comfortable environment where we are living together. And indoor is exactly the way you are saying. The students fall asleep in the classroom. Sometimes we complain about the teachers. The teaching quality, the content is terrible. Otherwise, the teachers complain to the students that they didn't sleep yesterday night because they go shopping.
We find the point.
Yeah,
It's carbon dioxide.
Yeah. And that is the reason we are actually working with the school authority to do this monitoring right now. Where the 5 or 6 big classrooms we are install some of the device right now, and we try to.
I also have the topics about the flow rate, the air change rate of schools. I found this topic still working, but I found in 20 meters squared, the space here,
20 meters square.
and you just suction, you just give the flow rate, the problem will solve. But the area is larger for 24
meters square.
meters square. That's another thing.
24 meters square. 20 meters square. How much for?
This is 6 meters. This is likely 10.
And that is 16 meters.
And, so 24 just like an office.
Yes.
Okay. So that is the big, that is the most suitable size.
So this kind of flow control is different from that way.
Okay.
So that's why I can answer your question.
Yeah.
Your classroom under D1 is so large. So not just simple to give an inlet and outlet to solve the problem. There we need to redesign.
But the cost is big, or can you have the
No, we just need big.
big money to?
Yeah.
Okay.
Because you need smart building, right?
Yeah.
Not a building with smart, right? Building with smart devices, right? But a new smart building, it's different, right? Different building. A smart building is cost a lot.
Smart building costs a lot. Yeah. You need smart control everything.
But we have the next step. It's called healthy building.
Healthy building.
It's more expensive. It's real because smart building is for engineering, thinking, everything in this building is smart with IoT, with artificial intelligence. But when you consider about the human health, you need the medicine care, you need the psychology care, you need anything. You need the sensor to detect the heartbeat, the blood pressure. Anything is expensive. So that's why public health is the future for engineering to make great economic.
Okay, we say thank you again for the very interesting and promising talk, and then we learned a lot, and then we need to cooperate with engineering to build a smart building and a healthy building, and then the expensive building as well. Okay. Thank you very much again, my